I don't know how many of you actually attempted to look for the answers. That many? Okay. I printed off like 40 of them. Hopefully they're enough. If not, I guess not. Wow. I have 2 left. Okay, so they're also on the website as of yesterday at some point. So anyway, do you have any questions? Homework or otherwise? Yes. 26 from 3.7. So we have the limit as x goes to infinity of x times tangent of 1 over x. And 1 over x, when you put it in infinity, you end up with 0. Tangent of 0 is 0. So you end up with 0 times infinity, right? So in order to attack this, we need to move one of the 2 parts in the denominator, right? And we can try either or, but as it turns out, the one that makes the most sense is to move the x on the denominator. Why does that make the most sense? Because we have tangent of 1 over x. So when you take the derivative, they'll actually end up cancelling out. So this is a situation in which we're looking at 0 over 0. So we have the limit as x goes to infinity of secant squared of 1 over x times minus 1 over x squared divided by minus 1 over x squared. As mentioned, the derivatives will cancel out, and secant of 0 is 1. Is that making sense? Yeah? Okay, what else? Yes?
Do we have a case where it turns out to be 0 or 1? Is that...
That's just 0.
Can you do me the
On 3.7?
Yeah.
We have the limit as x goes to infinity of the natural logarithm of the natural logarithm of x divided by x. So if you put in infinity for x, you end up with ln of infinity, which is infinity, or I should say ln of infinity, but nonetheless it's still infinity, right? So it's going to be infinity over infinity. We take the derivative. What's the derivative of ln of x? One over ln of x times 1 over x divided by 1. Right? And what is 1 over infinity? Zero times 0 over 1, which equals 0. Right? Is that making sense? Okay. What else? Yes.
2b or 3.6.
Okay. Well, let's do this in a particular order. Are we done with the homework? Oh, was that a homework? Oh, I'm sorry. I thought he was actually from the outline.
No.
2?
Yeah. 2b.
2b.
3.6.
Uh-huh. Two b. Hyperbolic tangent of 1? Okay, what's the problem? Hyperbolic tangent is defined to be... Well, what happens when you put in 1 for x?
I get it, need 1.
You get 1?
Yeah, well, no, when I get 1 for, I basically get e over e when I plug everything.
Are you sure?
No.
So hyperbolic tangent of x is defined to be e to the x minus e to the minus x divided by e to the x plus e to the minus x. Right? Okay, so hyperbolic tangent of 1 is just going to be e minus e to the minus 1 divided by e plus e to the minus 1. And if you want to be creative with this, I guess you can multiply and divide by e. Not necessarily that it's going to help you out, but you can write it as e squared minus 1 over e squared plus 1. But that's all there is to it. Bless you. You don't have to do the last step. I just...
Well, wait, what happened to the 1/2? They cancel out whenever you do that. And hyperbolic.
Mm-hmm. Is this making sense? Okay, what else?
Number 20, 3.7.
Okay. What's secant of 0?
0.
What is secant of 0? 1. Secant is 1 over cosine. By the way, secant and cosecant are both 1 over sine or 1 over cosine. As a consequence, they'll never be 0. Does that make sense? It's 1 over, some function. That can never be 0, right? So since secant of 0 is 1, there's really nothing to do in that problem, is there?
It's just 0, right?
It's just 1 minus 1 over 1. So it's just 0 over 1, which is 0. Remember, this is what I was telling you about L'Hopital's rule. Don't blindly start taking, the derivatives of this. Make sure you actually are in a 0 over 0 or infinity over infinity case. Okay? What else?
On 6.
30 on 2/6? Okay, so f of t is equal to e to the t times hyperbolic secant of t. So f prime of t is going to be, bless you, we notice it's a product of two functions, so we need to apply the product rule, the derivative of the first times the second. So it's just e to the t times hyperbolic tangent secant of t. Bless you. Plus the derivative of secant or hyperbolic secant is. If we don't remember, we look it up. Right? So we're going to have minus e to the t, hyperbolic secant, hyperbolic tangent.
That's it? You don't do anything else to it?
That is it.
Okay, so you don't want us to substitute anything?
Sorry?
You don't want us to put the e back in? You want us to leave that alone? Like, you don't want us to substitute like 1 over...
It's fine.
Like, swap cosine.
That's fine. I guess it does simplify nicer. But whatever.
Let's not.
If you factor out an e to the t hyperbolic secant, you end up with 1 minus hyperbolic tangent. And if you actually write what hyperbolic tangent is and get a least common denominator, the e to the t's will cancel out. So you'll just be left with 2e to the negative t over e to the t minus e to the negative plus e to the negative t. But I wouldn't worry about it.
Boy. So 3.6 is just kind of plugging in stuff, just looking back at the chapter.
Yeah, as I told you, I'm not going to spend too much time on this. You know, I mean, I basically gave you the homework. You can look at the derivatives, you know, when you write them out. The only thing that I want you to be aware of is what is, you know, hyperbolic sine, hyperbolic cosine, kind of like, you know, what exactly do they look like. And that's pretty much it.
Okay, for the test, are we going to have to memorize what the derivative of an inverse hyperbolic secant is?
What did I just say?
I don't know what you said.
I said the only thing you need to worry about this section is I want you to understand what hyperbolic sine and hyperbolic cosine are. Period.
Okay.
For the rest, I'm not really going to worry about it because I don't know them. If I don't know them, I'm not going to expect you to know them. I don't find it necessarily to be that useful at that point. If you look at the outline that I gave you, I think the only two derivatives the only two derivatives that show up from this particular section are u and v are hyperbolic sine and hyperbolic cosine. Those are the only two ones that actually show up there. Okay, anything else? Should we tackle the review? Okay. So let's see. Let's, I guess, set up some ground rules. First things first. The material that's going to be covered in the test. You're looking at, to quote from the syllabus. By the way, as I said before, or I don't know if I said it or not, but I made a mistake when I wrote the syllabus as far as dates are concerned. If you look at the actual date for the second midterm, it's supposed to be tomorrow, but that's obviously not the case. The exam is going to be on Wednesday, same class time, same as everything else as before. Okay. I was using the schedule from a previous class I taught, and for some reason those are the two dates that I didn't change, the 26th and the 28th, which are Tuesday and Thursday, I guess. But anyway, the exam says it's going to be out of sections 2.5 to 3.5. What actually will be, the test will be out of sections 2.5 to 3.7, which means what? Well, it's kind of ironic, the fact that I have written there that it's up to, okay, so 2.5, okay, let's go and look at it for 1 second, since I'm kind of jumping around. 2.5 deals with the chain rule, right? If you look in the outline, you're going to have the first problem deals with just taking derivatives, and as you notice, they're basically pretty much every single one of them requires the chain rule to solve. Now clearly it's not written in the test or in the notes, but it's kind of implicit that since 2.5 is actually on the test, 2.4 is also on the test, even though it's not actually written there, right? Because 2.4 was product rule and the chain rule and the quotient rule. Well, obviously when you're going to apply the chain rule, you're going to have to apply product or quotient at some point in time. Anyway, then we have 2.6, which is implicit differentiation. I'm assuming you noticed there's problems in there from implicit differentiation. We're going to have one related rate problem in the test. I know everybody's really excited about that. And then the last section from the chapter was 2.8, which dealt with linearizations and differentials. I would not worry about that section. So let's just make it official. 2.8 is not going to be on the test, since I assigned a whole 3 problems from that section anyway. Moving to chapter 3, the one thing that you're not going to find on the test, and we talked about this in the past, is section 3.4. So I'm not going to give anything from 3.4, and we already talked right now about what 3.6 is going to be, right? So what's the derivative of sinh? Cosh. What's the derivative of cosh? That's 3.6. Is that making sense? Yes.
We need to know what sinh is in terms of these.
It would be helpful, not necessarily for the test, but that's basically, kind of the real applications of them are, because they're in terms of the exponentials, but I wouldn't necessarily worry about them. Okay, so with that being said, what would you like me to do?
Differentiation problems.
Implicit differentiation, sure, yes.
We're just going to go through the review, then we're going to ask questions.
Whatever you guys want me to do. The reason why I gave you the outline on Friday was so you can actually work on these problems over the weekend and not wait until me actually doing them for you. Because, again, I can sit here and re-lecture everything that I lectured in the last 5 weeks. Hopefully, I actually know it since I'm the teacher. The whole point of it is for you to actually work on things and make sure that you figure out what you don't know. So that being said, that's basically why I took that particular approach. So we can cover whatever you think needs to be covered, whatever you think that you're not necessarily very good at that point. So that being said, yes.
Can you do problem 3C?
3C, sure. Do you want me to go in a particular order, or should we just jump around through things? Okay, so problem 3C. I just got tired of writing things. That's why I just said problem 140. Page 140. So page 140 says problem 47. At what points on the curve y equals, so let's see, 47 on page 140, y equals sine of x plus cosine of x, 0 is less than or equal to x is less than or equal to 2 pi, is the tangent line horizontal. So at what point is the tangent line horizontal? What should that tell you that we need to do? Bless you. Tangent line horizontal means the slope of the tangent line would be 0. which means what we need to find is at which points is the derivative 0. Is that making sense? Okay. So then what is dy over dx?
Cosine of x minus sine of x.
Cosine of x minus sine of x. So we set that equal to 0. Right? Then how do we solve that? Well, this is just equivalent to saying cosine of x equals sine of x. Right? If you want to be creative with this, you can divide by sine or you can divide by cosine. Right? If you divide by cosine both sides, you end up with tangent of x equals 1. So you have to figure out where the tangent is equal to 1. If that's going to be easier. If not, just think about for when is cosine equal to sine. Well, based on their alternating nature, the only times that are going to be having the same values, in magnitude anyway, is going to be at multiples of pi over 4, right? Because that's when both of them are square root of 2 over 2. Now they both need to have the same sign, and as it turns out, the first and the third quadrant is where they both have the same sign. And so x equals pi over 4 and 5 pi over 4. Is that making sense? The restriction that x is between 0 and 2 pi ensures that we don't have to actually list them all with, the plus 2k pi that you all love so much. Okay, what else?
One L.
1L. So f of x is equal to the natural logarithm of x divided by 1 plus the natural logarithm of 2x. So what should we notice? We're looking at a ratio, so we need to apply the quotient rule, right? The derivative of the top, which is 1 over x, times the bottom, which is 1 plus ln of 2x, minus, and now what is the derivative of 1 plus ln of 2x?
2 over 2x.
2 over 2x, or just 1 over x, right? Divided by 1 plus ln of 2x, quantity squared. Right? What's my answer? Aha. How did I get to that answer?
What are you asking me?
If you look in the answers that I have, that's not what I have, right? Before I continue on, let me ask you a question. What is the derivative of ln of any constant times x? Notice that using laws of logarithms, this is the same thing as the ln of a constant plus ln of x. Ln of a constant, the derivative of a constant is 0, so we can just end up with 1 over x. Right? This is what we would like to employ above. So if you look above, I can write this as 1 over x times 1 plus ln of 2 plus ln of x minus 1 over x ln of x divided by 1 plus ln of 2x squared. And notice that if you look up there, I'll have 1 over x times 1 plus 1 over x times ln of 2 plus 1 over x times ln of x minus 1 over x times ln of x. So those two actually cancel out. So we're just left with that. Right? Is that making sense? Okay, what else? For D and for F. We have the square root of xy is equal 1 plus x squared times y. And we're supposed to find the derivative by implicit differentiation. So we take derivatives in both sides. What do we get on the left hand side? So 1 over 2 times the square root of xy times. What should we observe now? What's underneath the square root? X times y, which means we're looking at a product rule. So it will be just y plus x dy dx equals 2xy plus x squared dy dx. Right? And all we have to do is just solve for dy dx. Right? Should I continue on or?
Yeah.
Okay. So notice first thing that we can do is, so we don't have complex fractions, I have y plus x dy dx is equal to 4xy square root of xy plus 2x squared square root of xy dy dx.
What did you just do?
I get rid of the, I got rid of the denominator, right? And from here, can I just write the answer? dy dx is 4xy square root of xy minus y divided by x minus 2x squared square root of xy. Is that what I have, or do I have them the other way around? I managed to match the answer. Right, you could have them the other way around, right? Y minus 4xy square root divided by 2x squared minus dx. Yes.
Okay, so you took the 1 over 2 square roots of xy, you flipped it and multiplied it by each term on the right side.
Yes. It's the least common denominator, so you multiply the entire expression by the least common denominator. Okay, what else? So, oh, sorry, set F. E to the x squared y equals x plus y. So again, if we take derivatives both sides, we end up with what do we get at on the left hand side? Sorry? E to the x squared y times 2xy plus x squared dy dx equals 1 plus dy dx. Right? So can I write directly what the answer is, or do you want me to multiply them out first? Okay. So we have 2xy e to the x squared y plus x squared e to the x squared y dy dx is equal to 1 plus dy dx. Right? Okay. So should I just write the answer? Or do you still want to see it factored and... Okay. So 2xy e to the x squared y minus 1 equals dy dx times 1 minus x squared e to the x squared y. Does that make sense? We're moving 1 to the left hand side, the quantity I boxed in red to the right hand side, and we just factor dy dx. Right? And so now dy dx is just 2xy e to the x squared y minus 1 divided by 1 minus x squared e to the x squared y. Which is the opposite of what I have. But anyway, is this making sense? Okay, what else? 5e. E, I see. The altitude of a triangle, so 17 on 131. The altitude of a triangle is increasing at a rate of 1 centimeter per minute, while the area of the triangle is increasing at a rate of 2 centimeters squared per minute. By the way, everybody remembers from geometry the altitude of a triangle is the same thing as the height of the triangle? Right? So what does that mean picture-wise? Remember what we said. Remember what I said about word problems, and especially related rate problems. Read the problem first to kind of get a feel for what you're looking at. Draw a picture and start putting things what you know in the picture. Right? So what do we know? It says the altitude of a triangle is increasing at a rate of 1 centimeter per minute. Right? We're not told about anything about the triangle, so it'll just be some random triangle, right? Is that making sense? The altitude is increasing at a rate of 1 centimeter per minute. So if this is my h, then dh over dt is going to be 1 centimeter per minute. While the area of the triangle is increasing at a rate of 2 centimeters squared per minute. So the area of the triangle is increasing at the rate of 2 centimeters squared per minute. At what rate is the base of the triangle changing when the altitude is 10 centimeters and the area is 100? So if we name this with the letter B, then we're asked what is dB over dt when h is equal to 10 and capital A is equal to 100. Is this making sense? Yeah? Okay, well I did the hard part. You solve it. this is taking all the information from the book, right? Remember the more or less mental steps that we were talking about, right? Read the problem, draw a picture, put everything you know on the picture. The next immediate step, which is basically the last step before actually doing just algebra, would be how do you relate your unknowns? How do you relate what you have with what you want to find? Area formula for the triangle. What does it say? Area is equal to 1/2 base times height. Right? So dA over dt is equal to 1/2 dB over dt times h plus 1/2 dH over dt times b. Is that making sense? You use the product rule, and you also use implicit differentiation, right? A, b, and h are all implicitly functions of time. On the right hand side, you have a product, unless you go between two functions, so you need to apply the product rule. Is this making sense? So now all we have to do is just algebra, right? What do we know? What do we need to find? What else? Is there any unknown that we don't have? So the thing we're asked is dB over dt, right? So we need to figure out what dB over dt is. So we can either plug in all the numbers we know, or we can actually solve for dB over dt, right? Which way would you prefer? Plug in. Okay. dA over dt is 2 is equal to 1/2 dB over dt times 10 plus 1/2 times 1 times, and now what is b? We know 100 is equal to 1/2 10 times b, right? So b is equal to 20. So times 20. So 4 is equal to, actually I don't know why I did that, but anyway, 4 is equal to dB over dt times 10 plus 20. So dB over dt is equal to minus 16 over 10. So dB over dt is equal to minus 1.6 centimeter per minute. Is this making sense? It's negative. Sorry? Area is 1/2 base times height. We're given the height and the area, so we can get the base. Is the fact that it's negative making any sense? Means the base is decreasing, or is the height is increasing, right? Would that make any sense? How would that be possible? The only way that would be possible is if your height is actually increasing faster than the rate the area is, right? The area is increasing at 2 centimeters squared per minute. The height is increasing at 1 centimeters per minute. So the point is the height is actually increasing faster than the area can actually catch up with, which means your base has to shrink to maintain that particular rate of increase for the area. Is that making sense? Okay. What else? So this Wednesday we have the second midterm, and I kind of set it up on purpose, even though it's going to be quite brutal as far as I'm concerned. But my goal all along was to give you the test on Wednesday and try my best to get your tests back by Friday. And it's set up on purpose in this fashion because Friday is the last day to drop the class. After Friday, you need the dean's permission to actually withdraw from the class. So I wanted to give you a little more information about where you're standing at that point. So I'm hoping I can actually get them done by Friday, but again, considering I'm dealing with 100 tests, that may or may not be very realistic, but I am going to try. And also I'm going to try and get all the grades, take the homework in, put it in, and basically try and come up with grade for the class for you, so you know kind of where you're standing at that point. But anyway, I kind of forgot to say this, so I figure I'll say it now before I forget again. So, what else? Another relay rate? Okay, which one? Is there any of them that we haven't done? Nine? I guess we didn't do 9, but that's just really boring. 11? We did 11, we did 13. I think I set up 15, right? I don't think I actually finished it. And then we just did 17, and I did 19, right? So I pretty much did all of them. Should we do, there's also chapter review if you want to be a little more creative. We can also look at the chapter review if you want to pick up one from there. You know, the one thing I told you about, this particular outline and in general, one of the ways to make sure that you get ready for the test is to make sure that you know how to do problems in general. And I'm giving you this particular outline not necessarily because I'm going to, on purpose choose problems from it, even though you probably saw that there were some in the previous test. But this is more or less the lines of making sure that you actually attempt problems in general and you know how to solve them. So obviously you don't have to do all 50 of them or how many they are, but you should make sure you do enough of them that you actually have confidence that you're doing them correctly or you know what you need to do. So that's why I said if you want to pick one from the chapter review, we can do that as well. It's kind of up to you what you want me to do.
11H.
Hold on, we're talking about related rates.
Oh, we are still?
67 on chapter review. A balloon is rising at a constant speed of 5 feet per second. A boy is cycling along a straight road at a speed of 15 feet per second. When he passes under the balloon, it is 45 feet above him. How fast is the distance between the boy and the balloon increasing 3 seconds later? So, as I said, we read the problem. Let's figure out how we set it up. Right? We have this wait a minute. Let's try and be okay, that's a balloon. Anyway, I guess it's actually just a balloon. I don't know, for some reason I thought about one of those hot air balloons, yeah. So I drew a hot air balloon. But anyway, so a balloon is rising at a constant speed of 5 feet per second. A boy is cycling along a straight road. So we have this lovely straight road. The boy is cycling on the road. So, let's see. Hey, not bad. Okay.
Keep going the other way though. Because he's already past the limit.
Well, he's going. It doesn't say which direction he's going, so I'm going to assume he's going that way. So, what do we know? Well, clearly, it basically starts looking like what we can have is a lovely triangle, right? So, okay, I'm facing some technical difficulties here. Okay, we have this lovely triangle, and so what do we know? Well, we don't really know much at this point, right? A balloon is rising at a constant speed of 5 feet per second. So if I name this side x, then I know that dx over dt is equal to 5 feet per second, right? What else do I know? A boy is cycling along a straight road at a speed of 15 feet per second. So if I name this side y, then I know that dy over dt is equal to 15 feet per second. Right? How fast is the distance between the boy and the balloon increasing 3 seconds later? So if I name this z, the question is what is dz over dt? 3 seconds later. Right? So far so good? Okay, so now let's relate all the rates. Z squared equals x squared plus y squared. Right? Take derivatives in both sides. I have 2z dz over dt equals 2x dx over dt plus 2y dy over dt. Right? I can cross out the 2's. So dz over dt is just going to be 1 over z times x dx dt plus y dy dt. Right? So I guess here comes the semi-challenging part of the problem. What happens, or what do we know, what do we need to figure out? We're given the dx over dt and dy over dt, right? Do we know what x is? Do we know what y is? Do we know what z is? For which? So what is y? Yes?
Doesn't it say when the height when the boy is under the
Well, we need something. We needed some sort of a measurement, and that's the measurement that we're getting, right? So when the boy was under the balloon was 45 feet up in the air, right? So what is x going to be? 45 plus 3 times 5, right? Is that making sense? What is y? 3 times 15, right? The boy goes at cycles at 15 feet per second, right? And it's been 3 seconds. So now, let's see, we get 60, and then we get 45. And so what is z? So what do we get? Let's see. 75? Right? I didn't actually compute it, if you're wondering why I came up with 75. 60 is 4 times 15. 45 is 3 times 15. So 15 can factor out, so z is just going to be 5 times 15, because Pythagorean numbers are 3, 4, and 5. So dz over dt then is going to be 1 over 75 times 60 times 5 plus 45 times 15, right? So let's see, 5 times 15, so I'm left with a 4, and then plus 9, so I end up with 13 feet per second. Is that making sense? And this is one way of going around it without using a calculator. Which of course I wouldn't necessarily expect you to do, but is this making sense? Yeah? So if you see a problem like this on the test, you know, that's a wonderful answer. Okay? As in, I'm confident everybody can figure out what 45 plus 3 times 5 is, which would be 60, and I'm fairly confident everybody can figure out what 3 times 15 is, right? As in what x and y are. But you don't necessarily have to guesstimate what the other ones are. Is this making sense? Okay. What else? Sorry? 9D. We're looking at y equals tangent of x to the power cosine of x. And I guess I forgot to write y equals for all the b, c's, and d of number 9. But anyway, you're asked to find the derivative of this. So the only way you can find the derivative of this is logarithmic differentiation, right? So we take ln's both sides. So I have ln of y equals cosine of x times ln of tangent of x, right? And so 1 over y dy dx equals negative sine of x times ln of tangent of x plus secant squared of x over tangent of x times cosine of x. Right? So far so good? Yeah?
Oh, wait. So for derivative of log tan x, we have 1 all over tangent of x on x.
Secant squared of x.
Secant squared of x. Oh, yes, the secant squared of x just moves on top.
Okay? Now, we would like to simplify things a little bit. And as it turns out, they simplify quite nicely. Secant is 1 over cosine, so this is 1 over cosine squared of x divided by sine of x over cosine of x times cosine of x. this whole thing simplifies to 1 over sine x. Can you see that? The cosine squared moves in the denominator. This cosine moves in the numerator, times the cosine makes cosine squared. And so the cosine squares will cancel out, so you're just going to be left with 1 over sine of x. Okay? And so dy over dx is just going to be tangent of x to the cosine of x multiplied by cosecant of x minus sine of x times ln of tangent of x. Okay? Questions? So the key idea is, if you see a problem like this on the test, which you probably will, if it's a function to a function, the only way you can take the derivative is if you actually take logarithmic differentiation. I don't want to see anything related to the power rule. I don't want to see, x to dx, the derivative is not x to dx to the, x minus 1 or some other combination of things. Is that making sense? Okay. What else?
How would you get from the sine x measurable in x and from sine x to
Well, 1 over sine of x is cosecant. That is that. Right? So the bracket is just the right hand side.
Oh,
And then I have 1 over y, which becomes that. Y is tangent to the cosine of x. Y is defined to be tangent of x to the power of cosine of x. So when you solve for the derivative, the 1 over y becomes just y on the right hand side, and you just write what y is. I just skipped a step, which apparently may or may not have been a good idea. Okay, what else? 10?
Yeah.
Which one? Sorry. D. So, if you see any of these problems involving a trigonometric function and an inverse trigonometric function, the first and foremost step you want to take is define the quantity in the parentheses to be some other letter. Now, we used y in the beginning, and then I started using theta, and I like using theta in general because it gives you the indication that you're actually looking at an angle, right? So if I let theta be tangent inverse of x, then this is equivalent to saying tangent of x, the tangent of theta is equal to x. And now we go to our right triangle. If I let that theta, that'll be theta. What do I know? The opposite has to be x. The adjacent has to be 1. Which means the hypotenuse is square root of x squared plus 1, or 1 plus x squared. So far so good? Okay? And so we're asked to find what sine of tangent inverse means. We're asked to find what sine of theta, and we just pick it up from the triangle, x over the square root of 1 plus x squared. Is that making sense?
It's okay to leave the
Well, that is the answer. And again, I said it at some point. If you are actually on the plan to take Calc 2, this is going to come back in the beginning of the semester a lot. So just be advised about that. Don't think that you're going to get away from it. As a general whole, this is what I was saying in the beginning of the semester. Notice how trigonometric functions have a knack of keep showing up as much as you love them. And remember them very vividly. Okay, what else?
Number 8C.
8C. Okay, so we're supposed to solve ln of x plus ln of x minus 1 is equal to 1. So what should we do? Okay. Be advised that if you apply e to both sides, you will not end up with x plus x minus 1. I solved this problem in class, 2 weeks ago or whatever it was, and I cautioned you at that point as well. The only way you can apply e's is if you actually apply it to the whole thing. So if I have e to the ln of x plus ln of x minus 1 is equal to e to the 1. Okay? Which you may not necessarily see how to approach it. So if you don't see how to approach it, you can actually start from the beginning and say I have two ln's, I can combine them and I'll end up with ln of x times x minus 1 is equal to 1. Which means x times x minus 1 is equal to e. The left-hand side, if I want to continue on, the only way I can get rid of the e's and the ln's is to actually realize that I have e to the ln of x times e to the ln of x minus 1 is equal to e. Which sends me exactly there. Is everybody understanding this? Yes? Well, then you're not really solving for x, right? Because you have x in both sides. Quadratic formula.
Oh.
X squared minus x minus e is equal to 0. So x is equal to 1 plus or minus the square root of 1 plus 4e divided by 2. Nobody said it should be out, it should be nice. So far so good? Are we done? We have to come back and make sure that both ln of x and ln of x minus 1 make sense, right? So first things first, notice that the square root is 1 plus something, which means the square root has to be bigger than 1, right? I'm assuming everybody knows the square root of any number larger than 1 will be larger than 1? Yes? Okay. So then this will always be bigger than 1. So 1 minus this quantity is negative, so that doesn't make any sense, right? Is that making sense? Also, you have x minus 1. So if I look at the plus, taking the minus 1 of it means just I don't have that. But the square root is still positive, so the second one makes sense, right? You could face a situation in which there is no solution. You actually work it out and you end up with no actual solution at the end. Is that making sense? Yes.
Alright, when we plug the e in, the square root, how come we don't make it negative e? Or 1 minus?
What do you mean? Here?
Yeah, right there.
What is the quadratic formula?
No, it's negative b plus or minus square root
Of
of b plus
squared
b squared.
minus 4ac.
Oh, it's minus.
Right? Yes? Okay. So answer is x equals 1 plus square root of 1 plus 4e divided by 2. Okay, what else?
Can you do
11e. Didn't I do that? On Friday? I mean, I'm kind of asking because, you know, sometimes I lose track since I teach 2 sections of the same class. Sometimes I do one problem in one class and I'm not exactly sure if I did it here or not, but I thought I did it. I mean, I can do it again if it's 11e. I did it? Okay. That's what I thought. I didn't remember for sure. So you want me to do it again?
Yeah.
Well, I mean, I guess you have it in your notes. Which one? D? I think I did D as well. For sure I did C. I did A. I think I did pretty much every single one of them. X to the x squared, I did that one. I did G. For sure I did I. I guess I didn't do J. Should I do J? Or you want me to do something else in the last 5 minutes? J? Okay. So we have the limit as x goes to 0 plus of the quantity cosine of x to the 1 over x squared. So remember, how do we approach these types of limits? First things first, what do we do when we see a limit? We plug in the value and see what we're looking at, right? Plugging in 0 gives us cosine of 0 is 1. 1 over 0 is infinity, so we're looking at 1 over infinity, which is undetermined, right? Right? Okay? So that being said, so I'll write this as 1 to the infinity, so we know what we're looking at. We're looking at e to the limit as x goes to 0 plus of the natural logarithm of cosine of x to the 1 over x squared. Right? So we take separately the limit as x goes to 0 plus of the natural logarithm of cosine of x to the 1 over x squared, which equals the limit as x goes to 0 plus of 1 over x squared times the ln of cosine of x. Right? So now, what do we do? Of what? What has to happen for us to take a derivative? Has to be 0 over 0 or infinity over infinity. Do we have that situation? Well, technically yes, if we notice that we can write this as ln of cosine of x divided by x squared. In this instance, we are looking at 0 over 0. Right? So far, so good? Yes? Okay. So now we're in the 0 over 0 situation. So we have the limit as x goes to 0 plus. What's the derivative of ln of cosine of x? Negative tangent divided by 2x. Okay? So what happens if I put in 0 for x? 0 over 0, so do it again. We have minus secant squared of x divided by 2. So we end up with negative 1/2. Right? Are we done? So the answer is e to minus 1/2. Right?
So where does that E come from?
Well, the only way you can start talking about ln's is if you have e to the ln. The problem is, if you just look at it right here, it's not an actual equation, so you can't apply ln both sides because there's no other side to be talking about. And so the only way you can approach it is to actually use the e to the ln identity. Okay? Well, then have fun. I will see you on Wednesday.